Odo pointed out yesterday to me, being in probability, it's way more easier than when you're talking in a deterministic setting about the future. So, what's our goal actually as stochastic modelers? Well, there are two extreme types of mathematical modelers. There are people who want to study nice probability theory and need inspiration for models and actually a real-life application for funding. Those people usually have a bias towards critical systems, and physicists' proofs are usually not enough for them. I don't know whether many of those people are here right now. Then there are the people who actually want to provide some contribution to public health. There are more people among you here in this class. They have a slight bias towards supercritical processes, so processes where actually an epidemic spreads. Because when things are critical or subcritical, well, not much happens anyway. And they are interested in quantitative results. They want to see how much effect there is from control measures and things like that. While the first class of people is mainly interested in qualitative results. Perhaps because it's the problems they're dealing with are so hard that quantitative results are beyond reach anyway. So I have could think of 5 directions of future research, which some of them were also mentioned 20 years ago, I think. Population dynamics and leaving the SIR framework. I will come back to that, of course. Spatial epidemics and percolation. And here long-range percolation comes in as well. Behavior change. How does that influence the spread of epidemics? And then there is the last 2 points I won't really go into, and I think Other will do it, about phylogenetics in epidemics and useful parameterizations of your epidemic models. So we usually look at, well, when doing branch process approximations, the populations we are looking at in which an epidemic spreads are usually static, and there is not much demographic turnover. Now we want to extend that a bit. So what if there is some demographic turnover, so births and death? So consider an SIR epidemic in your favorite structured population. So households, networks, whatever you like. And now we allow for individuals to die and be replaced by susceptibles. So here we make some assumptions. Everything is neat. As soon as someone dies, he is immediately replaced by susceptible. This model is close to SIRS epidemics, the model. And I want to stress this. This is not. This makes life much harder, because when we do branching process approximations, we are usually looking at R0, probability of a large outbreak, the final size of an epidemic, and we can ignore time. We can do the computations without looking at the dynamics. Things become much harder if we cannot no longer do that. SIRS epidemic is not even trivial if we look at, or is not even, I don't know whether there are results actually for SIRS epidemic on a line where people can only infect their neighbor. So things are definitely really hard if we go onto two-dimensional space, and I will come back to that. So in this open problem, so consider that we have a square lattice and we have a Markov SIRS epidemic. So everything can be represented in rates, and we have a given recovery rate and a given rate of regaining susceptibility. So someone who is recovered from the epidemic gets susceptible again at a given rate. It is not known for this model, and this might be surprising, that where the probability of a large outbreak is non-decreasing in the infection rate. So if we increase the infectivity of the disease, will actually the probability of getting something bad increase as well? Not known. Not even known if it's possible to define a critical value below which there is no epidemic possible and above which there is an epidemic possible. So getting more infectious is not necessarily leads to something worse. This open problem is quite challenging, given that there are papers about mentioning this problem by Rick Durrett and co-authors, and Jeffrey Grimmett, Rob van den Berg. So people working in percolation theory and interacting particle systems, the top people working there, look at this problem. Of course, things can get challenging as well when we look at dynamic populations, where, for example, we assume that in a household population, individuals can die, newcomers come in, there is migration between households. And in a network population, we can look at the same. Individuals can die. Of course, all friends of that dead individual lose a friend. So their degree distribution, or their degrees change. And there can come the new kid in town who also infects, can play a role in infection. This plays actually quite an important role in the spread of sexually transmitted diseases, where the new people come in, people after some time get monogamous, so they don't spread that much anymore, things like that. A lot of modeling needs to be done here, and from a mathematical, the rigorous part, I think not much is done yet. For household, if we look at those models in households, then if households are all large, multi-type population models can be used. So the type of a individual is just the household in which he is. Then we can do something. If households are of moderate size, troubles appear. Even in static household models, probabilities for final sizes in the SIR model are quite terrifying. We can express them in an elegant algorithmic way, but if you look at the expressions itself, they are huge, and if you get to households of size 10, they don't fit on A4 paper. Well, that's perhaps a bit too much, but but the computer can do a lot. But if there are dynamics, then we have to keep track of the real-time dynamics, and that's not nice. Well, let's say it's challenging, and that might be nice, but not nice for applied people, I would say. So we get the question, how long does an epidemic restricted to households last? It's quite hard to say. So one thing I want, which is manageable perhaps, is it possible to create household structure or population dynamics in which actually the expressions become a bit nicer so that we can actually do things, apart from all household size too. Now, for dynamic networks, we can say the network itself needs to be studied. What are the asymptotic quantities of a dynamic network? And epidemics on that asymptotic network are, or the dynamics on that asymptotic network, asymptotic static network, are they the same as on the dynamic network? Can we find some relations there? And of course, here the epidemic is influenced because of new connections to susceptibles. On a finite network, epidemic will always, SIR epidemic will always die out. If an epidemic can grow forever, or if a network can grow forever, the epidemic might go on forever as well. Some modeling is possible in Markovian network models. Tom Britton has already done some things, and together with China Turova and some co-authors, and this is still going on. Now we go to R naught, and here I want to say something which is probably insulting to all of you. So I want to discuss what is R naught. Hans did already something 21 years ago. That was not before I was born, but it was definitely before I was scientifically born. So I just go quickly through it, and I will come to something new. So please bear with me. So we go to a graph representation of an epidemic. So in uniformly mixing population, n individuals are represented by n vertices or nodes or points, whatever your language is. An edge is drawn from the vertex representing the initial infectious individual to every individual it contacts. So basically it's just a graph representation on how the infection spread. And from the vertices at graph distance k, so those individuals connected to the initial infected individual are generation 1, and from generation 1 we draw vertices, draw connections to other individuals, and if those other individuals were not yet in the graph, they are generation 2, and we go on forever like this. Now the start of such an epidemic in a uniformly mixing population is well approximated by a Galton-Watson branching process. Frank did a lot of work on that. And again, the initially infective is the generation 0 individual, neighbors are generation 1 individual, and then go to generation 2, and so on. Now the basic reproduction number R naught is the expected number of generation 1 individuals. And this R naught is useful for vaccination, and as a threshold, if R naught is below 1, we won't see anything happening actually. If it's above 1, we might see an epidemic. Now we look a bit further. So we had this graph representation of the epidemic. Now let's set k be the number of generation k individuals in this branching process, and bk is the number of individuals within the first k generations. From branching process theory, we know that if R naught is larger than 1, then the number of individuals within the first k generations divided by R naught to the power k converges to something, and converges to something non-trivial. This is nice, because from this we can define R naught. Well, first we want to send the population size to infinity, and then we look at how many individuals are infected within k generations, take that to the power, or take the kth root of that, and we get something like R naught. Actually, perhaps Hans would argue this is not really R naught. In that case, call it R star, if that makes it makes you happier. But this definition actually leads to R naught in uniformly mixing populations, but also in multi-type populations. And also, it makes sense for networks. But now we go to space. So we consider a square lattice, or a triangle lattice, or whatever spatial structure you like. And we consider that you cannot spread epidemics for more than farther away than distance m. Then the number of individuals you can infect within k generations grows quadratically in k. If you take that to the power 1 over k, then we see that with our definition of R naught, we get something which converges to 1. And this is an important message I like to give to non-mathematicians or public health people. If you are working with a disease and your estimate of R naught is close to 1, then probably your model is wrong. So at least I would recommend to consider that. And also, if you are looking for example to the triangle lattice, then if you use, for example, pair approximation or other moment closure techniques, well, those methods are useful for some networks, but not for a purely spatial network as the triangle lattice. Then there are other methods which don't give any quantitative results, but just don't do it. That's when you have a spatial epidemic, don't use R naught. I want to stress that this is just for spatial epidemics. With Stephen Davis and Hans, we had a paper on the spread of plague where we used percolation theory. And a year later, I was at a workshop in Italy where a speaker didn't know that I was in the audience as well, but he referred to our paper saying that we showed in our paper that R naught doesn't make sense. That's not what the message of the paper was. In some models, in some epidemics, R naught doesn't make sense. That's my message. So in general, R naught does not make sense or is useless in spatially organized population, and long-range percolation can be used. So I come to what long-range percolation is. So consider a square lattice with nearest neighbor edges. So now I go to percolation at first. For each edge, so we have an infinite square lattice, we flip a biased coin. If heads, which has probability p, we keep the edge. If tails, probability 1 minus p, we throw the edge away. In that way, we have a remaining graph. Now, we can look what's the probability that the origin is in an infinite cluster. Well, that probability we call theta p. Now, the questions of interest are, will there be an infinite cluster? And is there a critical value of this p at which we keep an edge, such that below that p we don't have an infinite cluster and above that we have? Well, answer is yes, in 2 or more dimensions. Is there an infinite cluster and will it be unique? And will it have positive density? And the answer is yes again. What happens at the critical value? Well, physicists know quite a bit. Mathematicians don't know that much, let's say it like that. And what's the value of PC? Well, there, nobody knows. But there is one exception. Harry Keston, one of the big shots in percolation theory, the critical probability, wrote a paper with the title, the critical probability of bond percolation on the square lattice equals a half. So if we are in 2 dimensions, we know what the critical value is. Why I want to show, also want to show the abstract of this paper, because it's, I think, genius. And here I suspect that Harry Keston didn't intend to be humorous. But it's very informative. Okay, now we go to long-range percolation. So we construct a random graph in the same way. We have a vertex set ZD, so cubic lattice. And now we don't have the connections yet. But for every pair of vertices, we just add an edge with probability p, which only depends on their distance. And we do that independently. And yeah, we can represent that in different ways. This is very interesting from a mathematical perspective. Newman, that is Charles Newman, and co-authors looked a lot at critical values, or the critical behavior. One interesting thing about this model in 1 dimension is that even at a critical value, so if that would correspond with R naught is 1, there is an infinite cluster. So even at criticality, an epidemic can spread. In more dimensions, this is not the case, and there is work by, well, perhaps I should say Biskup, Berger, and Beniamini, all those great Bs in probability theory, on how supercritical percolation works in this case. And how fast epidemic can grow depends on lambda r, but here again, we can only give bounds on it. We cannot give any real numbers. And the bounds are basically 1 plus epsilon and 10 to the power 100. So that's about how precise we can get. So for practical purposes, perhaps this is not useful. One can try to get that upper bound a bit lower. So how can we work further on it? So Valerie already talked a bit about spatial graphs. So what if the population is not a lattice? Or what if it's not a homogeneous Poisson process? Can we extend to that? For long-range percolation, qualitative results might be interesting. What do real populations and networks look like? We always assume, or most people work in epidemiology, use models which allow for an R naught. And my suspicion is that there is no biological reason for that. It's just mathematical convenience. And so we can actually question whether how does an epidemic spread in real life? What do real networks look like? Do they allow for exponential growth of an epidemic? What if our estimates for R naught are close to 1? Well, perhaps our model is wrong. There is one exception. There might be some self-organized criticality. That's a hot item in, or was a hot item in physics. Per Bak, who introduced it in physics, wrote a book with the humble title, How Nature Works, on this topic. And can we do anything with SIS epidemics, dynamics in space or on random graphs? There again, we need way more precision And if the Markov property is lost, things become very hard. So I will go very quickly into behavior chains, and then I will spend one line on phylogenetics and epidemics. What if we have a new frightening disease around? Then people perhaps stop traveling, or governments will take measures, close schools. What will happen then? It will lead to changing parameters in response of the epidemic, so not seasonal or things like that. So here again, real-time dynamics are important, which give quite some challenges for a rigorous mathematical modeling. And the duration of an epidemic is very important. And since parameters are changing, things becomes harder as well. And it becomes even more harder or more interesting, depending on your point of view, if people take measures depending on what they observe in their neighborhood. If an epidemic spreads to the neighbors only, and you take decisions based on what you see in your neighbors, then things become nice. So here you can see ring vaccination for animal diseases. So you vaccinate everyone around infected herd. And if information spread on networks along the same channels as the disease, what can we do then? Is there some relation with competing disease models? No, and on phylogenetic and epidemics, I just want to say a lot of discussion is coming up in Oberwolfach in November, I think. And some people of you might be there. Okay, this was it. Thank you.
Great. Thanks, Peter. I think that will keep you busy for 20 years. Doing all this research. Are there comments by people or questions?
That was great. Question for Valerie, and this is from a user of some of the moment closure methods. Are we going to be able to get away from so you do the moment closure stuff on the microparasites, you end up with some moments, and then you have to actually say, well, let's assume it's negative binomial, okay, to get at the actual distribution, to get at the zeros, which is what the empirical people really care about often. So are you going to be able to give us a better distribution than the negative binomial? It's a bit more mechanistic.
Well, yeah, I guess that the distribution is I mean, it's not coming out of the model at all at the moment.
No.
So it's a question of trying to find a way of doing the modelling to work out what the distribution actually is. We use negative binomial because that's what the experimenters tell us is the appropriate distribution, or some nearby approximation.
But is there some Poisson mixture that would be, could come out of the model?
Just stand here because people in the back can't hear, I think so.
Yeah, you might want to repeat the question, actually.
Oh.
Sorry.
Brian is asking if there's a better way of dealing with macroparasite approximations than assuming a negative binomial distribution and using moment closure with to give you the parameters of that distribution. Is there? And my answer was that which isn't an answer really, but I think we don't have a model at the moment to give that negative binomial distribution, except we've got general arguments about why a negative binomial distribution is appropriate, but it's not coming out of the stochastic model in any way that corresponds to the particular parasite which you're trying to fit. So there's a gap there which needs filling rather, and I'm not sure.
Well, we do have the odd model which deals with things like that, very specific.
Yes.
And the answer is not negative binomial, but I can tell you what it is.
But getting that distribution in general is going to be.
Is there any general?
What is your general model? Yes, I mean, you have to consider a lot more than just, numbers and classes. You have to know numbers and classes with levels of infection and so on.
Question for Peter. Some of this is what you talked about. It's not my area. So, why would it make a difference if you have an infinite cluster? I mean, you start out with an infinite matrix. When you said, well, sometimes you have an infinite cluster and sometimes you don't. But why would that make a difference?
Yeah. Here, I should have
Could you repeat
explained.
the question, Peter? Because
Okay.
I think for the back.
So the question is, if you start with a square lattice, for example, why are you interested in an infinite cluster? Well, here we can come back to the graph representation of an epidemic, and if a connection is preserved, that actually means that you infect, that if the starting point of that edge get infected, then it will also infect the neighbor. And in general, either the clusters will be small, and then I mean really small, or they will get infinite. So an infinite cluster will correspond to a large outbreak. And yeah, in general, we are not that interested in the small outbreaks because that's only marginal on the world population. But large outbreaks are interesting. And well, of course, initially percolation theory was introduced by mathematicians who don't care about epidemics at all. But
Thanks.
I'm not sure whether I've understood fully the ramification of the difficulties of defining R naught for spatial models, but is it fair to say that it's basically comes from trying to fit a spatially homogeneous model to a spatially structured process? In which case, I wouldn't see a deep reason why one shouldn't be able to come up with reasonable generalizations of the definition of R naught also for these spatial processes. There's, for example, there's lots of work on traveling waves and traveling fitness waves, and clearly there's growth at the tip of the wave, and so the definition of R naught would itself have to be spatial, but shouldn't it be possible to define something reasonable like R naught also for the processes that you mentioned?
Yes. Oh, sorry. Is it possible to define something like R naught for a spatial epidemic? That's more or less the question.
Yeah. The thing where your R naught went to 1, right? So
Yeah,
you
yeah.
said this was obviously nonsensical, and I agree. But
Well, as long as it's corresponding to the idea of R naught, which was, among other things, appears in Hans's thesis, I think it's not possible to define such a thing in a locally finite setting in space. I have heard people define R naught as, well, we have an infection rate in space, and we divide it by the critical infection rate, and that's our R naught. That makes sense. Of course, in this case, the critical value is R naught is 1, because that's how we define it. But my suggestion is then not to talk about R naught, but about the critical infection rate. Why taking that extra step about talking about R naught? Because that R naught, which I just suggested, has also nothing to do with critical vaccination rate or something.
Can't you still count leaves on the infection tree if you're an SIR? That's what Matt and I had to go do.
Sorry?
So Matt and I had to go at this definition where you count, you still count generations like you did at the start. So you can still do that in space,
Yeah,
as long as you're an SIR.
yeah.
So I think you can start can still define a counting model that isn't related to rates with dimensions of 1 over time.
But won't that go to 1 anyway in space? Then we have a discussion point for later.
But maybe this can help. My personal understanding of it is that when the concept of a node makes sense when you have geometric growth or an exponentially growing phase in your epidemic. So whenever you have a growth that is less than exponential, for example quadratic if you have a square lattice, then our node doesn't really fit in that definition. So that's all. If you have models where you don't have exponential growing phase, then our node will be 1.
So that's very true. But say, for example, this comes from just something spreading, and then of course the growth is not exponential. If I take the whole area, if I look at sort of the propagating front, there it's still a locally exponential process.
I totally take your point.
Your exponential, fitting an exponential would quite literally be okay, except that the fitting space would have to move with a wave, so to say.
We're splitting dictionary definitions here, really. I mean, if you go back to before R naught became sort of established in its sort of present meaning, I mean, it was originally the number infected by a typical infected individual. And the more abstract definition of the power law things, so we assume exponential spread, is fine, but it is one of a family of critical parameters, and since that now has the name R naught, we need something different for spatial models. But we can still go, seems to me it makes a lot of basic sense to go back to how many people does a typical infected individual infect, and then I think taking up something you said, Peter, maybe to say, well, okay, if we can identify a critical value for that, then beyond that, higher values, I mean, we could think of something, a parameter that is twice that, if you could take out at random half the population and the disease would still manage to spread. So so you can get a sort of multi-effect there. So I'm not saying there's any one particular definition, but I think there are probably several sensible definitions for spatial processes. But I think what you're really saying is that remember that R naught is a critical parameter, and if we have populations where the disease typically grows exponentially, then there's a particular definition which is the accepted one for R naught, that's a good critical parameter. If it's something like spatial, then, or other graphs where growth is not going to be exponential, we need to look for a different sensible critical parameters.
Okay.
Sorry, I think the problem in that case is that it's not very easy to identify a typical infected.
Yeah.
Because if you find a clear definition of typical infected, then you find R naught basically.
No, but in a spatial model, there's a basic parameter is if you have a homogeneous process where everyone has same distribution of number of neighbors, you can just say how many of those do you infect on average, okay? And then one of the most basic things with a spatial model is that the critical parameter there is going to be something significantly bigger than 1.
More questions?
Well, I mean, since still was about your definition of R naught, I don't know if maybe it would take too much time. I just was curious about when you construct this kind of degeneration, so you construct the edge, depending on the neighbors, and then you talk about within an infectious period. So you assume that is not a random variable. You assume that will be given.
Okay.
Correct?
Yeah.
So can you say something when that is actually random?
Yes, it will be. So what if the infectious period is not fixed? There is quite some work being done on that. I think it started with Karikou Lasma in 1982. And here I have to say that in the literature, some people drifted away by a false statement in a much cited paper, let's say it like that. So in general, if the infectious period is random, then epidemic will spread less as compared if we take the marginals of the spread. So we can say something about it in a qualitative sense. Doing computations on a random graph is a lot harder. But yes, we can say something.
One question. All these models on graphs or lattices or anything, are they really relevant for human populations and contexts? Since the edges are usually not fixed and most of the results that are known would not survive a dynamically changing graph organism.
This is like I would say not as relevant as many people claim, and perhaps not relevant at all. But I say this having in the back of my mind that I've worked for more than 10 years on those kind of models, so I'm a bit hesitant of saying that it's not useful at all.
Do not worry, because I worked for more years on less relevant.
Peter, you had on one slide you had something you didn't address called useful parameterizations, which was something that you see as one of the 5 things for the future. Does it mean you can distinguish between useful and unuseful parameterization? What did you mean by that?
Well, I can be short about it. This is also about ongoing work which Tom, Frank, and Pieter Trapman and Jean-Stéphane Deschamps in France are working on. That often we model epidemics in terms of infection rate or underlying network structure as and like it's nice to model those things with a given structure, a given infection rate, but those things we don't observe. What we usually observe is perhaps an infection profile, but not by looking at the infectious load or viral load of people. Perhaps we can get some information of that on that. We might observe the Malthusian parameter of an epidemic if it's exponentially spreading. But that's about it. We don't observe social structures among which an epidemic spreads. Perhaps for sexually transmitted diseases, where we can define what a contact is in some sense. And yeah, for computer viruses, where there are actually messages sent, or for animal diseases where there is transport of animals. But for human populations, we don't have a clear clue about what the population structure is, even household models. Like, do we take households in context? Do we look at households only? Do we look at households and workspaces? Do we look at households, workspaces, and the supermarket one visits? With SARS, households, workspaces, supermarkets, and funerals one attend. Yeah.
Okay, thanks. Then we go for coffee and tea, and the bell will ring when it's over.